Greetings! So back to the paging problem. And still we are dealing only with deterministic algorithms. So there is a proposition, theorem, however you wish to call, theorem. There is no deterministic, and this is absolutely important here, so no random involved, same input, same output, online algorithm for the paging problem. With the competitive ratio better than K. Even if n is K plus 1. So what does this mean? This means that if the size of the cache is K and you have a deterministic online algorithm, it might be K competitive, it might be K plus 1 competitive, it might be 2K competitive, whatever. It can be no competitive at all, just if seen for the LIFO and the least frequently used algorithms. But there is absolutely no possibility that it's better than K competitive. So in the worst case, you will end up spending at least K times more money or movement costs than it's strictly necessary. Okay, now how do we prove such things? We will have two statements. First, for each algorithm A, or I'll say such algorithm, so deterministic online algorithm, for each such A and input size or input length M, there is some bad enough input on which A will miss the cache all the time. Meaning on which the cost of A is M. And for this input, we'll also have n equals K plus 1. So of course, if n is larger than K plus 1, then you simply don't have to use all the pages and you just use the first K plus 1 pages and that's all. So we can generate a bad enough input, but it's not enough. We have to show that the optimal cost is around M divided by K, and this will be the second statement, that for each input say sigma of length M, and n equals K plus 1. So I will say that the optimum is around M divided by K. And to show this, it's enough to say that the longest forward distance, that was an offline algorithm, remember, and I told you that this computes the optimum. The LFD sigma cost is at most. So it's k plus, say, m minus k over k, the ceiling. So it's just make it rounded upwards. And of course from these two statements we will get the result, because then the algorithm divided by the optimum cost for this input, because for every input this will hold, and in particular for this bad input as well, the algorithm's cost will be at least as large as m divided by k plus m minus k over k. Right, so here I am using this one, and since the denominator is larger, it will make the fraction itself smaller. And this guy here, m divided by k plus blah blah blah, since k is constant, this will eventually converge to, say, m divided by m over k, which is just k if m goes to infinite. So you can try this if you just plot this function, for example, if you haven't learned enough calculus to do this, but this fraction will just converge to k, which means that there is absolutely no possibility that the algorithm has a strictly better competitive ratio than k, because eventually this series will exceed anything which is lower, which is smaller than k. Okay, so let's do this. Let's try to prove. Say, this is easy. So the first one, bad enough input, it's simple because the algorithm is deterministic, so it's enough to always ask for the page which has just been discarded, to always request the page that has been discarded. We can do this, discard it. Well, of course we have to initialize somehow the sequence, so we just after starting with the usual sequence of 1, 2 and so on, k plus 1. Yeah, because if you always request the page which has been discarded, well, even if you don't know the inner state of the algorithm, there is a possibility. So the input sequence itself exists even if you cannot really construct it, and since it exists, it has to be taken into account. So for example, against FIFO, the first in, first out, I will just ask for 1, 2, blah blah blah, k plus 1. Now at this point, k plus 1, we will, the FIFO will discard the page 1, so I will ask for 1, which is not in the cache at this point. And then FIFO will discard the 2 from the cache, and then I'm just asking for 2, coincidentally. And then it discards 3, and so on. Blah blah blah. Reaching k plus 1, I will ask for 1, 2, blah blah blah, k plus 1 again. Now this is a bad input for FIFO. For other algorithms, another algorithm will be the worst one. So for example, for the LIFO, we have already seen that bad enough input was just constructed exactly this way: 1 2 blah 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 k plus 1, and since k gets discarded, it's k and then k plus 1 and so on. K plus 1, k plus 1, k plus 1. So the actual bad input sequence, of course, depends on the algorithm itself. But still, for any algorithm which is deterministic, I can generate such a sequence. So since the same input always produces the same action sequence, the same output, it will be one of the worst cases, which will actually have a cost of m. So that's fine. Now for the second statement, second part of the proof, for each input, the longest forward distance algorithm's cost is at most this one. If you don't remember what the longest forward distance algorithm is, then it's a good point to recall this by rewatching the video, the previous one. So I will just show it by an example. So for example, what do we do here? So for example, if I'm getting, for say for k equals 3 and thus n equals 4, I will have, okay, so let's start with 1 2 3 4 1 1 2, well, 3 4 1 3 2 2 1 4 3 4. That will be enough. So what happens if we run the longest forward distance algorithm on this particular input? Here the cache is empty. I'm only writing down the cache cache contents. So it's 1, it's 1 2, it's 1 2 3, right? The longest forward distance. Here I'm drawing a line. I'll call this part an end of some phase, say it's a 3. Now then 4 arrives and I have to decide which of these 3 elements to discard. So far the algorithm spent k cost. It might happen that, say, here I also have a 1, the cost will be also k. So basically when all the k plus 1 different elements arrive, the phase will end just before getting the k plus 1. So here 1 is here and 1 is here, 2 is here and 3 is there, so 3 is the farthest amongst these guys. So 1 is immediately requested, 2 is requested 3 steps later, and 3 is requested 4 steps later. So the longest forward distance algorithm will discard the 3 and make the cache to be 1, 2 and 4. Now I will mark this guy and of course these guys, only the first ones, so the cost of k, and here I spend the cost of 1. But then 1 is in the cache, 1 is in the cache, 2 is in the cache, and 3 is not in the cache because I just discarded it. Remember, this was a point, the latest possible, when I just checked all these elements. Now here 3 is not in my cache, so I again drawing a line marking the end of a phase of a part of the input. I'm always marking an end of a phase when I am discarding a new element according to the longest forward distance. And now I'll again check. I have 1, 2 and 4 in the cache. 1 is here, 2 is there, and 4 is here immediately. So amongst these guys 2 is the farthest away, so I will discard 2 and I will have 1, 3, 4. I discarded the 2 and loaded the 3 which was just requested. But now again Here is the 4, it's in the cache. Here is the 1, it's in the cache. Here is the 3, it's in the cache. And then I arrive to this 2, which was just discarded because it was the farthest away. So I mark again an end of this phase, and then I'll have to pay for this one. And amongst these 3 guys, 1 will be used here next time, 3 will be used there next time, and 4 will be used there next time, meaning amongst these guys 3 is the farthest away, so I will discard the 3. And then I will have 1, 2 and 4. But then again, 2 is in the cache. Right now I'll just put this here. 2 is still in the cache. 1 is in the cache. 4 is in the cache. And 3 is not in the cache, again because this was the farthest point. And now I'm again marking an end of a phase. Here I will pay for this guy. And then I'll have to check the occurrences, but 1 is absolutely not occurring later, 2 the same, and 4 will be here, so I'll discard either 1 or 2. Probably I will just settle with the 1 because it's smaller, it doesn't really matter. So here I'm paying for this 3, and then I will have a final configuration of 2, 3 and 4. But then again, I won't pay for this guy here because it's in the cache. Now in general, such a phase, and what a phase here is important, in such a phase there are exactly k different elements, right? Here 1, 2 and 3. Here there is 1, 2 and 4. Here there is 1, 3 and 4. Here there is 1, 2 and 4. And here this is the last phase. The last phase possible doesn't contain 3 different elements, right? Now, but all the other phases will contain k different elements. Why? Because here in the bound of a phase, in the end of a phase, there are k elements. And there is this k plus 1th element which just arrived and it's not in the cache. These guys together are all the elements, so it's always the 1 blah 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 k plus 1. That's why we are at the end of a phase here, because this guy is a new guy and these are k different guys, and in total I have k plus 1 different elements, so that's all. Which means that if amongst these guys, say in this example 2 is the one which occurs the latest, this means that all the others, say 1 and 4, will occur also within this phase. So within this phase the last one won't appear, so in this case this 2 won't appear here in this segment. But all the others will, because they precede this element. That's why we choose this guy to be discarded. So this means that all the other k minus 1 elements occur here. In this case 1 and 4 occur here. And also there is this very new element in the very beginning of the phase, which might happen more times after that, but it means that there are exactly k different elements in each section, which means that the length of each section is at least k. Now in this case all of these sections had a length of k plus 1, but in general it doesn't have to happen. So for example, if I just leave out this one, or just leave out this 3, or just leave out this 2, then each of these phases will have a length of k and the phases will be the same. So the length of each phase, but the last one, the length of each phase the length of each phase is at least k. And for in each phase, but the first one, in the first one I will spend k cost. Cost is k. But for all the other phases I will just pay once, because a new cache miss will mark the beginning of the next phase. So in each phase I pay only one amount of money. This is an important property of the longest forward distance algorithm. In each phase the cost is exactly one. Of course, in each phase after the first, right? So it's in all the other phases, which means that here I'll have cost of k, and the number of phases here is, well, so in total there are m inputs or requests, and the total number of phases is at most so there is a first phase of length at least k, and then we originally had m requests, and we still have at least m minus k requests after the first phase, because the first phase is also at least has length of at least k, so we will have at most m minus k remaining requests, and each of these guys is at least having a length of k. But the last one, so I'm just rounding it up, and that's the number of phases. And in each phase I will spend some amount of money or cost. So in the first phase I will spend an amount of k, but in all the other phases I will just spend one cost for each phase. So that's why the longest forward distance will pay at most this amount. The longest forward distance on any sigma which has n equals k plus 1, that's important, is at most k plus m minus k over k. So in this case, for example, this expression gives, say it's m equals 18, so what it says that the cost of LFD, the algorithm's cost, is at most, so it's 3 for the first phase plus 18 minus 3 divided by 3 rounded up, which is so it's 15 over 3, so it's 8. And if we just check, the actual cost is 3 in the first phase, okay, so it's 3 in this case, plus 1, 2, 3 and 4, so it's 7. So indeed it can be smaller than that, but in general the optimum cost is at most this amount in general, while the algorithm might pay m for this, and as we've discussed it before, where exactly? We discussed it here. we discussed it here. This means that so the optimum, the LFD's cost is at most this one, while the payment of the algorithm is M, which means that it will converge. If sigma gets longer and longer and longer, it will converge to K, which means that there is absolutely no online algorithm, deterministic one at least, which can beat the competitive ratio of K. Now, in the next part, we will see that the LFU algorithm is K competitive, but it will happen only in the next episode. Till then, bye bye.